I'm with Veryst Engineering. We're an engineering consulting firm, actually just 3 exits down from here for 128. We do, I think, very sophisticated nonlinear multiphysics simulations and testing for a wide variety of industries. The value that COMSOL brought in this investigation was the ability to handle a complex heat transfer processing simulation in a small period of time, because we had to get an answer quickly, and COMSOL provided an opportunity for us to do so. This example was associated with process industry and involved the startup of a processing plant which used anhydrous ammonia and had specific piping associated with that. I put a little picture of the piping line and something from an MSDS sheet which talks about the dangers of that particular chemical. Upon startup, when this plant was commissioned, anhydrous ammonia immediately started spewing from the area which we show in the photograph, from a valve which consisted of a body and 2 end caps. And large quantities of the anhydrous ammonia were released. People were in the area, there were injuries, and the question is, what happened? How could this have happened? And what can we do to prevent it in the future? We were asked to investigate this, but once again, this is a process facility. They wanted to try and get an answer quickly. So this is just another picture of the valve indicating a center section and 2 end caps. The ball valve sat in the center, the end caps closed it off, and there were gaskets which sat between those 2 pieces. What's a little non-standard associated with this valve construction is that it actually had a connection which, instead of being threaded and combined, was actually welded. So the valve was welded to the piping rather than threaded or connected in any other way. And this is just another illustration from the end on showing the weld. So a pipe would literally be inserted into the end cap and then welded around to provide a, ultimately permanent and tight seal which wouldn't require maintenance. The issue is, though, if you look at the installation instructions for this valve, it says weld by applying a recommended 1/8 inch weld bead per pass. So you can do multiple passes, but each pass has to be 1/8 of an inch in size. Caution, do not heat the center section over a certain temperature, and actually be proactive about that by monitoring the temperature and actively cooling that center section to prevent overheating. But if you look at the weld in this case, on the right-hand side, I have an example dimension of 1/8 inch. The actual weld, which was a single pass weld, was actually 3 times that size. And the question is then, well, that's true, but could that have provided some explanation of why the leak occurred? This is a cross-section, a schematic cross-section of the valve. Excuse me. There's a center section, there's an end cap, there's this is split symmetrically, well, no, the other side end cap, excuse me, is not included in this image. The pipe comes in, and then there's a weld bead between the pipe and the end cap to provide the connection, and then there are seals. The seals are compressed by bolts, so when the valve is assembled, there is both a graphite and a PTFE, a Teflon-like polymer, which is compressed to provide the seal. That is delivered and then welded as in whole. And the reason why you control the temperature is pretty obvious. We have polymer components inside, and we want to prevent those polymer components from getting too hot. So the question was welding the culprit? This is a passage from one of the leading texts on fluoropolymers. Actually, Jorgen Bergstrom and I authored the chapter on mechanical analysis of fluoropolymers in this, but this is not from that chapter, but it states that stress relaxation is an issue. For example, a gasket under pressure, and these are pressurized, can creep, which leads to reduced bolt pressure, and that can cause leakage. So there's a known mechanism, there's a known deviation. Now, can we see anything based on our investigation which would give us insight? We know the materials which go into the valve. So we built a COMSOL model. We used SolidWorks, built the model, ported it into COMSOL. This is just the weld in a highlighted to illustrate where it is. This is a cross-section with a point pointed to the PTFE gasket, which provides the major sealing. The graphite was not the major sealing interface. And this is just an exploded view of the same structure, which shows the location of the gasket. Okay. So really the question is, when you weld it well, properly, or you don't weld it properly, what happens to the temperature of the gasket, and what does that do? Because we want to maintain the seal in the valve. We performed 2 sets of analyses. One with the weld as manufactured, one as it should be recommended, but we had the problem that the valve in question had long since been disposed of. It was considered to be deficient. The plant threw it out. So we didn't actually know what the size of the weld bead was. We didn't know what the welding parameters were used for that process, so we couldn't get an answer. We had to bound it in some way and see what that told us. So we looked at both large weld, recommended weld, and then we also did it under different, 2 different welding conditions in terms of the size of the fusion zone. We've done welding analyses. We've done welding analyses to look at residual stresses, microstructural changes. We've incorporated nonlinear material properties to look at the development of those residual stresses. This is a simpler analysis than that because we had a short period of time to be able to do this work. We did, however, include radiation, conduction, and convective cooling. We included the effect of the radiative heating from the plasma arc from the welding torch. We used COMSOL's equations to be able to represent the rotation of the fusion, the welding process around the circumference of the valve, both in terms of radiation and the deposition of molten metal. We included superheat and temperature-dependent material properties. This is just a little animation of the fusion zone translating around, which we've accelerated for purposes of viewing. No one would weld this fast. The actual welding process took 30 seconds to a minute to move around the weld circumference, but you can see we simulated both low and high penetration in terms of the size of the fusion zone, and then we did it for 2 different sizes. So that was a representation of the fusion zone, just to get a sense. This is for the 1/4 inch, so this is the too large weld, and this is just the temperature field which develops as a result of that processing. Okay. So this is the temperature field which develops, and once again, the weld is moving around. The point to look at is the gasket location, and the maximum temperature is 200 C. And remember, the temperature which it should be reached is no more than 176. And we were conservative in these analyses. I'll do this again, which is we bias the analysis to lower temperatures so that any error that we would introduce would indicate, if we exceed that temperature, we know that the actual temperature was actually probably higher than that. So the welding arc temperature we chose to be 4,000 C. That's a very low estimate in terms of the temperature of a plasma arc. It could be 10,000 or more. So under this circumstance, under this size of the fusion zone, we're immediately and easily exceeding the maximum temperature which is recommended for the valve. And if you look at the creep information for PTFE, it creeps at these temperatures. You will have a relaxation of the compression of your gasket under those conditions. And now with a maximum temperature indicated at 160 C, if we go to the gaskets, we never reach that temperature because you can see it heats and then it convectively cools and conducts the heat away. What was so useful with COMSOL is we were able to do this in 2 weeks. That trying to do this in a different code would have been just longer. It wouldn't have given us an opportunity to give information to our client in a timely manner to be able to understand, because their safety organization needed an answer. There had been injuries associated with it. They weren't going to take actions until they had an explanation. Another explanation, however, was that the valve wasn't assembled properly to begin with, that the bolts weren't tightened, and therefore they'd come with delivered a defective product. So we'll get to that in a second. So this is just a repeat of what we said before, but when we plot the maximum temperature in the body of the valve, and this is sort of on the other side of the gasket, under the conditions of too large a size, even under conservative conditions, we were able to see that we were exceeding the recommended temperature. Therefore, providing certainly a plausible explanation for why this leak occurred. And this is just a table which represents that same result. Remember, the temperature was supposed to be 176, and even under conservative conditions, we exceeded that. And then the question is are we right? We do an enormous amount of simulation, but we also do an enormous amount of validation. And therefore, we took valves, we welded them, we tested them. So we took valves, we welded them according to the recommended procedure, where we cooled the body of the valve during the welding, kept the weld bead below a certain size, fabricated them, sealed them, and tested them. Under correct welding conditions, we were able to test 20 valves, all being leak tight. We then removed one bolt completely. So there are 4 bolts holding it together. We loosened one entirely. It was still leak tight. But because creep could occur, we then waited a certain period of time, which was longer than that associated with the fabrication period at the facility, and it was still leak tight. Because we didn't know exactly what the welding conditions were, the plant did validate that if they had welded it, if they did an extreme case of welding, that they could lose pressure and the valve would leak. But their main concern was if we do it properly, or can we trust the structure? So what was the consequence? The consequence was very quickly using COMSOL, simulating what 20 years ago would have taken a long period of time. We were able to get rational results which provided actionable recommendations. The plant went back, retightened all of the valves, no further problems, and what COMSOL provided was a straightforward, complete analysis, providing an explanation which was visualizable, communicatable, and to us made sense. So, thank you very much.